Mathematical induction. What is mathematical induction, one may ask? Mathematical induction is a proof technique that consists of two parts. The first part is a base case, and the second part is the inductive step. And in the inductive step, we have something called inductive hypothesis, which is just a fancy name for assumption. Okay, so a good way of illustrating this proof technique would be the example of a person climbing up the stairs. So if we wanted to show by induction that this person can climb up the stairs, so first what we need to look at is a base case. And what we need to show is that the base case holds. And pretty much in this case, a base case would be showing that this person can reach the first step, which means that P of 1 holds. And in this case, P of 1 is a proposition person can reach step 1. Now we look at the inductive step. So in the inductive step, what we want to show is that for all k, if P of k holds, then P of k plus 1 must hold. So here what we're doing is that we are assuming that this person over here can reach step k, right? So we are assuming that P of k holds. And then based on that assumption that P of k holds for some arbitrary value k, we want to show that P of k plus 1 must hold, meaning we are assuming that this person can reach this step over here, and based on that assumption, we want to show that this person can reach the next step. And that's it for the inductive step. So pretty much, this is how a proof by induction works. P of 1 holds, and if P of k holds for some arbitrary value k, then P of k plus 1 must hold, which is the inductive step. And once we've shown those two, then we've shown this holds for all n. One may ask, is the base case always 1? The answer is no. It depends on what the problem is telling you. Now let's look at an example. So this example is saying let n be a positive integer, shows that every 2 to the power of n by 2 to the power of n checkerboard with one square removed can be tiled using right trinomials. Okay, so we're going to prove this by induction. A proof by induction, remember, consists of two parts, meaning we're going to have a base case and an inductive step. So let's start with the base case. So for the base case, we're going to let n equals to 1. One may ask, why is n equals to 1? The reason is that n is a positive integer. And by definition, we know that positive integers are greater than or equal to 1. So for this reason, we have n equals to 1. And in the base case, what we want to show is pretty much that this statement over here holds for n equals to 1. Okay, so how are we going to do this? So we're going to draw a picture. Since n equals to 1, meaning we have a 2 by 2 checkerboard. And very important to note, with one square removed. So I chose to remove this square over here. I mean, it could have been any square. So if you remove this square over here, clearly this can be tiled using a right trinomial. Therefore, the base case is true. So now we've shown the base case is true. So now we're going to look at the inductive step. Remember, in the inductive step, the first thing we're going to have is our inductive hypothesis. And in this case, what we are going to do in our inductive hypothesis is assume that the statement above holds for some integer k. Okay, so pretty much all we are supposing is that a 2 to the power of k by 2 to the power of k checkerboard with one square removed can be tiled using right trinomials. And remember, with a proof by induction, right, in the inductive step, I want to suppose it holds for some arbitrary value k, which is what we've done. And what I want to do is show it's going to hold for k plus 1. So now we're going to consider a 2 to the power of k plus 1 by 2 to the power of k plus 1 checkerboard with one square removed. Okay, so one may ask, how am I going to show that a 2 to the power of k plus 1 by 2 to the power of k plus 1 checkerboard can be tiled with one square removed? Remember, whenever I'm doing a proof by induction, right, I always want to use my inductive hypothesis. And in this case, what is my inductive hypothesis saying? That's right, it is saying that a 2 to the power of k by 2 to the power of k checkerboard, meaning somehow I want to transform this 2 to the power of k plus 1 by 2 to the power of k plus 1 checkerboard into checkerboards that are 2 to the power of k by 2 to the power of k. As you can see on the picture over here, we have a checkerboard that is 2 to the power of k plus 1 by 2 to the power of k plus 1. So let me draw it out. So this side over here is going to be 2 to the power of k plus 1 as well. And we want to use our inductive hypothesis, right, which consists of 2 to the power of k by 2 to the power of k checkerboards. And how are we going to do that? So as you can see on the picture, we're going to need to split the checkerboard. And here, if we split it into 4, right, so we first split it horizontally, and then we split it again. So we're going to end up with 4 checkerboards of 2 to the power of k, right, by 2 to the power of k. Okay, so far, so good. But remember, our inductive hypothesis is telling us that the 2 to the power of k by 2 to the power of k checkerboard has to have one square missing in order to be tiled, right? In order to say that we can tile it. And remember, so here we know that a 2 to the power of k by 2 to the power of k plus 1 checkerboard, right, has a square missing, which is this square over here. However, this 2 to the power of k by 2 to the power of k doesn't have a square missing, this one doesn't as well, and this one doesn't as well. We want to somehow take away a square so that we can use our inductive hypothesis. And how are we going to do that? That's right. So we're going to place a triomino in a way that we're going to remove one square from each, right? Which is this triomino over here. So we're going to place it in such a way that we're going to have one square missing here, and one square missing here, and one square missing here. And now simply all I'm going to do is apply my inductive hypothesis, right, on each of these square, and I can tile them all, right? Because here we have one square missing, right? That's part of the problem. So we can tile this by applying the inductive hypothesis on all the 2 to the power of k by 2 to the power of k checkerboard on all 4 of them. Therefore, we can tile it. And we've shown that our inductive step holds. So we can say, therefore, right, by induction, you can tile a 2 to the power of n by 2 to the power of n checkerboard, meaning this holds for all n. Because by definition, if you show that the base case hold and the inductive step hold, then you've shown that by induction that you can tile the entire thing is going to work for all n.
Strong induction is a proof technique that consists of 2 parts, the basis step and the inductive step, which includes the inductive hypothesis. Let's look at an example that shows these concepts. Suppose we can reach the first and second rungs of an infinite ladder, and we know that if we can reach a rung, then we can reach 2 rungs higher, proof that we can reach every rung. First, let's look at the basis step. In this example, our base case is going to be n equal to 1. In the basis step, we want to show that we can reach the first step. For the inductive step, we have the inductive hypothesis, in which we assume that we can reach any particular rung between 1 and the kth rung for some positive integer k. For example, if k equals to 20, then we could reach any particular rung between 1 and 20. Once we have the inductive hypothesis, we must show that if p of 1 and p of 2 and p of 3 all the way to p of k holds, then p of k plus 1 holds true for all positive integers k. In other words, once we have proven the base case and the inductive step, then we can say that we can reach any step on the ladder. Therefore, we can climb the whole ladder. One important thing to note is that we can always use strong induction instead of mathematical induction.